Section 9.2, Solving Quadratic Equations by Graphing. What we're going to see in this section is a way to solve a quadratic equation that's based on a lot of the skills we developed in the last chapter, which was graphing quadratics. In general, if we have an equation of the form ax squared plus bx plus c equals 0, that's our quadratic equation. That's called a nonlinear equation, and it's written in standard form. Now it's called nonlinear because the graph of the function that equation is connected to would not be a line. The exponent of 2 on the x tells us that that's going to be the case. We know the graph of this would be a parabola, which we saw in the last chapter. Now, in order to solve this by graphing, there are 3 steps. First, we graph the related function, which is y equals ax squared plus bx plus c. Second, we determine the x-intercepts, if there are any. And then 3, the x-intercepts are the solutions to the equation. And that's all that it is. So just by looking at the graph, we'll be able to determine the solutions to the equation. So we can save ourselves some algebra. Now, we don't have to use standard form. Just a little note down here. We don't have to use standard form to graph the function. Oftentimes, that's going to be the way that it's presented to us. Vertex form, though, would work just as well if we happen to have it written in vertex form. Intercept form would not really work or need to be used because the point is to find the x-intercepts, and so once we do that, once we have an intercept form, we have the x-intercepts, so there's no reason to graph at that point. It still could technically work, but it would be more work than we need to do. Alright, let's start to take a look at a couple of examples. Alright, so we're going to start with kind of a basic example here. X squared plus 2x equals 3. The first thing I'm going to do is I'm going to move all the terms to one side so that I have my equation equal to 0. Now, it doesn't matter which direction I move it to, but certainly it seems easiest to move just the 3 here. So I'm going to subtract 3 from each side of my equation. Now, on the left side of my equation, I'm just left with x squared plus 2x minus 3. I can't combine any of those terms. They're not like terms, so I just have to leave them like that. And on the right side, I want to make sure that I say that equals 0. And now I'm going to replace the 0 with a y, so I'm going to say, usually I change the order now, and I have y equals x squared plus 2x minus 3. And so that right there is a function, y equals x squared plus 2x minus 3. And I can graph it using any of the techniques that we did in the last chapter. Use x equals negative b over 2a, find the axis of symmetry, find the vertex, plug in other points, and you can generate your graph. Or you could use GeoGebra or some other graphing software. So since this is not a lesson on how to graph, let's just see what that graph would look like. So we can see what this graph is. It's a parabola that opens up, has a vertex at -1, -4, and it has the domain and range that we'd expect, and we're good to go. It has the y-intercept that we'd expect, which is -3. But anyways, the point of this is to solve the original equation, and that's to determine the x-intercept. So I look here at my 2 x-intercepts, where the parabola hits the x-axis, which we also call the zeros of the function. And the 2 values that I get are -3, 0 and 1, 0. Now what I'd be looking for are my x values. And so I'm thinking here that my 2 solutions are going to be x equals -3 and x equals 1. And those are actually both going to be solutions here. I'm going to end up with 2 different answers. It's important, however, to check our solutions. So what we do is we take one at a time. We take one of the values of x and we plug it into our original equation. So for the first one, I'll check the negative 3 here. I'm going to do negative 3 squared plus 2 times negative 3, and I'm hopeful that this equals 3. Well, negative 3 squared is a positive 9. 2 times negative 3 is negative 6. And it certainly looks like 9 minus 6, that does equal 3. So that one works. I'll let you check the other solution on your own. X equals 1. You can check that out just by plugging that in. But it should end up working out. And those will be the two solutions to your original equation. So kind of a nice, convenient way to do it based on some skills that we already have or using some technology. All right, let's take a look at another example here. We've got solve x squared equals 8x minus 16. We're going to follow the exact same process. Now, once again, I can choose to move everything either to the left or to the right as long as I leave 0 on one side. It doesn't really make a difference, but I prefer to keep my x squared as positive. And so as a result, I'm going to decide to move the 8x by subtracting that from each side. And I'm going to add 16 to each side. That's going to make it easier for me. I like having it that way. So I'm going to do x squared minus 8x plus 16 equals 0. And then, like I said, I replace that 0 with the y. So I'm going to have y equals x squared minus 8x plus 16. So let's take a look and see what the graph of that would look like, again using the techniques that we've used in the last chapter. Alright, so what we see here is we have a parabola that opens up with its vertex at 4, 0, which also happens to be the x-intercept. We only have one x-intercept here, which is different than the last problem. Now, I did mention that I could have moved the x squared to the right instead, in which case I would have had y equals negative x squared plus 8x minus 16. And if that was the case, then my parabola would actually be almost exactly the same. It would actually just be upside down. It would be a parabola that opened down, and it would have the exact same x-intercept. And that's always going to be the case. The x-intercepts will stay the same here. It's not going to matter which order we move things around in order to graph them. But anyways, here we graphed the function and we figured out that it has one x-intercept, so we think that the x value there is going to be our solution. So I think that x equals 4 is going to be our one solution. And before I confirm that, let's just plug in to check. I'm going to plug into my original equation. And that's important. You always want to plug into your original equation in case when you move things around you made a little bit of a mistake. This will be a way to check out that you've got it right. So I'm hoping that 4 squared will equal 8 times 4 minus 16. Well, 4 squared is 16. 8 times 4 is 32. And 32 minus 16, yeah, that works. That is 16. So I have my solution here. Now what we're going to see in the coming sections is just because we have one solution here, it's actually kind of an important thing in algebra that whatever the degree of the polynomial, in this case 2, whatever that degree is, that would tell us the number of solutions we should have. So it looks like we only have one solution. But as it turns out, x equals 4 is actually two solutions in one. It's what we call a repeated solution or a repeated root. There are two solutions, but both of them are 4. It's something that's going to make a little bit more sense in a couple of sections, but it's something just to keep in mind. Figured I'd mention it now. All right, let's try one more example. All right, last example here. I'm going to solve negative x squared equals 2x plus 4. Let's follow all those same steps that we have been. Once again, I have my choices to which side to move things to. I'd like to keep my x squared positive, and in this case it's already negative, so I'm actually going to move it to the other side in order to make that happen. And when that happens, I get a 0 equals, and I can assume or assign the order that I want, x squared plus 2x, it's positive there in front, plus 4, and replace that with y. So I get y equals x squared plus 2x plus 4. So once again, x equals negative b over 2a, axis of symmetry, vertex, other points, connect them, and there you go. You'll get all the points that you need, and then you can graph your parabola. So let's take a look at what the graph would look like. This is definitely different than what we'd expect. Here we have a parabola with the vertex of negative 1, 3, and it opens up. It has a range of y is greater than or equal to 3. It has no x-intercepts. We can't even do step 4 because it doesn't intersect the x-axis. We've seen parabolas like this before, so it shouldn't really be a big surprise that it could happen. Whenever we have a parabola that is either above the x-axis opening up or below the x-axis opening down, it has no x-intercepts. The function has no zeros, and therefore the equation that it came from has no solution, or more specifically, no real solution. I mentioned before that the degree would tell us how many solutions there are. There are still 2 solutions to this, but they're not real numbers. There's something called imaginary numbers, which we'll be looking at later on, maybe in this class, maybe in Algebra 2. But the bottom line is there's no real number we can plug in and make the left side of the equation equal the right side. So it's a little tough. We can't really check this one. Step 5, we kind of have to ignore. We can't really check it. But whenever you graph and you get a parabola without any x-intercepts, like this example here, we can say that this equation has no real solution, or just no solution. Alright, so just want to kind of wrap things up here. If we take any quadratic equation and rewrite it where we get 0 on one side, we can graph a function that's related to it. And based on the x-intercepts that we find, we can identify the solutions to the equation. We always want to check, because sometimes it looks like certain values, the x-intercept, and it might actually be off a little bit. Maybe it looks like it's exactly 1, but it could be 1.1. So we always want to double check. If the related function has 2 different x-intercepts, like this example here, then the quadratic equation is going to have those 2 solutions at the x-intercept x values. If the quadratic equation has 1 x-intercept, which happens to be actually at its vertex, which would be in this case 4, 0, x equals 4, then it's only going to have 1 repeated real solution. So that's a different case there. And then the third case is that a graph of a parabola has no x-intercepts, like this example here. Then that quadratic equation is going to have no real solutions. And that pretty much wraps up everything you need to know about section 9.2. There are some applications we're going to look at, but that is all you need as far as new material goes. Hope this was clear.